In this video, we're going to look at the ways of multiplying vectors together. We're actually just going to concentrate on the first way here, the scalar or dot product. I'll briefly introduce the vector cross product, but we're not going to be using it this quarter unless we look at torques, and when we get there we might use it. So we'll worry about that then. Okay, the scalar or dot product between two vectors yields a scalar as the result, and the reason that we call it the dot product is because we just have a simple raised dot between the two vectors, and that signifies it. And the result is just a number. And so now the number may have units depending on what the units of the vectors happen to be, but the result is this. It's the magnitude of vector A times the magnitude of vector B times the cosine of the angle between the two vectors. And so if you imagine A is a vector pointing this way and B is a vector pointing that way, then the angle between them is phi, is what I'm using for it here. So now, because of a particular property of the cosine function, if you measure the angle from B to A or the angle from A to B, you may think that you'd get opposite signs on that thing, and actually you would. If typically we measure counterclockwise in the XY plane to be the positive direction for angles, and if you go clockwise, which is in this direction, you'd get a negative value. However, the cosine function has this property. If this is theta on the horizontal axis, the cosine function is symmetric about the origin, left-right symmetric at least. And so let's see, this would be out here at pi over 2. This would be pi there. This would be minus pi over 2, or minus 90 degrees, and I can't draw worth beans, but this would be at minus pi. But anyway, the cosine is symmetric either side of there, and so it doesn't matter if phi is positive or negative, you'd get the same result for it. And because of that, the dot product is commutative. So B dot A is also equal to magnitude of A, magnitude of B, cosine of phi, and that's equal to A dot B as well. So this is a commutative multiplication. That's not the case with the vector product, which we're not going to use in this quarter, but to do this I have to kind of make three-dimensional representations of vectors, and they do this in your textbook probably better than I'm going to do. But if this is vector, I'll just pick different letters here. This is vector Q and this is vector N in this direction. The cross product of Q into N turns out to be a vector. That's why we call it the vector product, and it is perpendicular to both Q and N. And Q and N determine a plane. Two lines determine a plane. You may remember that from geometry way back. But this would be the direction of the vector Q cross N, and in fact that's the way we denote the cross product, or the vector product. We use this little big X, or just an X symbol between them. It's raised off the line a bit, but that's the symbol for the cross product, and it produces a vector Q cross N. And if you take Q cross N going that way, that's the vector you get. But if you take n cross q, and there's q, there's n. N cross q is a vector, oh, let's see, going in this direction. It's harder to draw, trying to make these things perpendicular. Anyway, it's perpendicular to both these vectors, and it points in the opposite direction. So q cross n is the opposite of n cross q, or it's the negative of the vector. Now, we're not going to do anything with this. This is the product that we're talking about today. And at first, we're just going to investigate this property that it's equal to the magnitude of A, the magnitude of B, times the cosine of the angle between them. Okay, we have a vector P that has a magnitude of 35 and a vector W that has a magnitude of 16. And the two vectors have a 28-degree angle between them. Find P dot W. So it's just going to be this. P dot W will equal the magnitude of P, the magnitude of W, the cosine of the angle between them, which in this case is going to be 35 times, now here I'm using a raised dot just to indicate multiplication, times 16 times the cosine of 28 degrees. You could do this in radians if you wanted to. You'd have to express 28 degrees in radians, but I'm just going to stick with degrees here. So anyway, in this case, this particular dot product is going to be 490. I can only keep two significant figures here, so for that particular dot product. Now, going a different direction, V has a magnitude of 13.5 and M has a magnitude of 63.2. If V dot M equals 128, what is the angle between them? Well, V dot M, V dot M is going to equal magnitude of V, 13.5, magnitude of M, 63.2, and then the cosine of the angle between them, and I'm just using phi for those angles. You could use theta or any favorite Greek letter you want to. In this case, that's going to equal 128. Well, I can find the cosine of theta from that, and I get that the cosine of theta is 0.150. Okay, well, phi is going to be the inverse cosine of 0.150. When I took trigonometry in high school, I learned to think this every time I was taking an inverse cosine. Actually, the way we wrote it in those days was to write the arc cosine. And when you saw that, you were supposed to think the angle for which the cosine is. And so I've trained myself when I see an inverse function like that, it's the angle for which the cosine is 0.150. And it helps me remember those things, or has in the past. I'm pretty good at them by now. I get 81.4 degrees for the angle between those two. Let's make that 81.4. How's that? Anyway, that's the way you can figure out the angle between things. Now, I haven't shown you how you might calculate this for a different sort of vector, but we'll get to that. We will get to that. P has a magnitude of 35 and M has a magnitude of 63.2. What can you say about those vectors if P dot M is equal to 0? Well, the dot product of P dot M is going to be the magnitude of P, 35, times the magnitude of m, which is 63.2, times the cosine of the angle between them. Which means, now this isn't the right number of significant figures, but I'd get 2,212 times the cosine of phi, but that's equal to 0. Well, the only way that can be 0 is if the cosine of phi is 0. When does that happen? Well, let's make our little sketch of the cosine function again. By the way, this is a handy thing to be able to do. Frequently, we'll be looking at sine or cosine functions and wanting to think about what they are at different values, and it's nice to just be able to draw a quick sketch of those things. And it doesn't have to be the greatest drawing in the world. This is going to come back up here. Anyway, where is the cosine 0? This is the cosine of phi as a function of phi. It's equal to 0 at either minus 90 degrees or plus 90 degrees. Well, if the angle between two vectors is 90 degrees, P and M are perpendicular, or in math speak from somewhat more advanced classes, we might say they're orthogonal. And if you take linear algebra, you may hear that. I don't remember ever hearing that term in calculus, but it's only been 40 years since I took calculus. I may have. I was taking first quarter calculus at the same time I was taking first quarter linear algebra at Eastern. There were 2 quarters of linear algebra at the time. You may start learning that term orthogonal. So if the dot product between two vectors is 0, they are perpendicular or orthogonal. Or if they're perpendicular, the dot product will be 0. So let's consider dot products of the unit vectors. And this will also let us learn something about the dot product of something with itself. So I hat dot I hat. That will equal the magnitude of I hat, which is 1, times the magnitude of I hat, which is 1, times the cosine of 0 degrees, because the angle between a vector and itself is 0 degrees. Well, that's just 1. So, which is the magnitude of that vector squared. If we did something like the magnitude of, or the dot product of P and P, we would get the magnitude of P times the magnitude of P, which is P squared, times the cosine of 0, which is 1. The dot product of a vector with itself is just its magnitude squared. That's kind of interesting. All right, well, there's I hat dot I hat. Turns out j hat dot j hat will also equal 1, and k hat dot k hat. We're not going to be doing much in the way of three-dimensional vectors this quarter, but I'm introducing them today just so we can see this consistent across the thing. That's also 1. Well, what about I hat dot j hat? Remember, I hat is a unit vector pointing in the positive x direction. J hat is a unit vector pointing in the positive y direction. And so here's the x-axis, here's the y-axis. They happen to be perpendicular. I hat points that way, j hat points that way. They're perpendicular, so I hat dot j hat is 0. Also, if you've got a z-axis, it points perpendicular to the xy plane. It's perpendicular to both those vectors. So I hat dot k hat is also equal to 0. Turns out j hat dot k hat is equal to 0. A unit vector dotted with itself is 1. So I hat, j hat, k hat, those are all equal to 1. and the sort of products with the other unit vectors are equal to 0. So this is going to be kind of a useful property here when we start calculating dot products of vectors written in component form. Okay, finding projections of one vector onto another. This is an interesting idea. It's something that is used a fair amount in engineering statics when you get to there. When I used to teach that class would be up to about 100 miles an hour on vectors in the first 2 days. And so it was kind of challenging for students who were trying to take it at the same time they were starting engineering physics. It's better to have the first quarter of physics under your belt before you take statics. Anyway, P has a magnitude of 35 and W has a magnitude of 16. They have a 28-degree angle between them. Find the projection of P onto W. And what that means is if I draw those two vectors, so this could be P, let's see, that was 35. W has a magnitude of 16, so it's shorter. Okay, and we have a 28-degree angle between them. Okay, but W, you can think of it as having a line of action that extends out in that direction. And the projection of P onto W would be taking this vector here and seeing what its component is in the direction of W. Okay, so the projection of P onto W this would be a right triangle in what I'm trying to do here. And got the magnitude of P. This would be the side adjacent to that 28-degree angle. This component of P projected onto W would actually equal P times the cosine of that angle that's between them. In this case, it's 28 degrees. Well, what that means is P dot W, which we haven't calculated in this problem, is the magnitude of P times the magnitude of W times the cosine of the angle between them. And I'm just going to make a note that phi is equal to 28 degrees here, so I don't have to keep writing that. Okay. Well, P cosine of that angle is this part, or if I take P dot W and divide it by the magnitude of W, I get P cosine of that angle. That will be the projection of P onto W. The next part, I'm supposed to find the projection of W onto P. Well, that would equal W cosine of that very same angle, which is going to equal P dot W, vectors up here, divided by P. Okay. So if I calculate P, the dot product of P dot W once, I can just divide it by those different parts and I'll have those projections. Once in a while we'll be interested in doing that. If we've got say a typical horizontal vertical coordinate system like X and Y, and we have an inclined plane, we might be interested in the projection of the weight. Maybe it's got a block sitting on it or something like that. We might be interested in the projection of the weight of some object, and I'll write W as a vector to represent weight. We'd like the projection of W onto the plane. That'll tell us the part of the weight that'll tend to push the thing down the plane. So we might do something like that. Although I'll show you what I tend to do when we've got an inclined plane is instead of using this for the coordinate system, I'll make one that has x pointing down the plane and y pointing perpendicular to it. But I may still end up doing some projections of things in certain directions. So we'll see how that works. We'll be doing a lot of different things with vectors this quarter, so get used to that. Well, let's calculate p dot w once and be done with it. P dot w, I'm just going to take the magnitude of p times the magnitude of w and multiply it by the cosine of 28. I get 490 for this. So the projection of p onto w is just going to be p dot w divided by w. So if I just divide that number by the magnitude of w, 16, I get 31 for that. So that would be the projection of p onto w, and it's actually almost twice as long as w, so it's going to extend quite a ways beyond there. And then the projection of w onto p, which would be making another imaginary little right triangle in there, doing something like that. That would also be about 490 divided by the magnitude of p, which is 35. And I get about 14 for that. So that's a way that you can find that. They do quite a few examples in the textbook of projections of things, different things onto the axes stuff. Okay, calculating dot products with vectors in component form, and this will be using the commutative and distributive property. The distributive property in mathematics is that if you have a times b plus c, you end up with ab plus ac. That multiplication of a is distributed between both the b and the c, so you get something like that. And commutative just means it can be done in any order. So let's take a couple of vectors and write them in component form. And I guess I could do it for a three-dimensional vector once, and then we'll call it good, and we'll stick with two-dimensional after this. Let's suppose that we have a vector n that is equal to, I'm just going to use integers on this one so the math can be done in our heads. 6i hat plus 7j hat minus 12k hat. So we've got a minus sign tossed into the mix, and you could try to imagine a little three-dimensional coordinate system and trying to get that. And then I'll have a vector q, which is going to equal, make up some simple numbers, 5i hat minus 4j hat minus 6k hat. Okay, so got these two vectors that are in three-dimensional space. Let's see if we can figure out what q dot n is. Now remember, this is commutative, so it's going to come out the same no matter what order I do it in. I'll write q first, which is 5i hat minus 4j hat minus 6k hat. This is going to be messy, so just get used to it here. There's that one, dotted with 6i hat plus 7j hat minus 12k hat. And I'm going to wrap these things individually in parentheses as I'm multiplying them together. But the first thing I do, I'll take this 5i hat and distribute its multiplication across all three of these things. So I'll have 5i hat times, or dotted with, 6i hat plus 7j hat minus 12k hat. And then I'm going to have minus 4j hat dotted with 6i hat plus 7j hat minus 12k hat. And then I've got finally, minus 6k hat dotted with 6i hat plus 7j hat minus 12k hat. Let me show you real quick what happens when we have a scalar like 6k hat, and that's a vector, dotted with another scalar, which is, I don't know, we could have 14j hat, something like that. Well, you take the scalars and multiply them together. Okay, so that'll be 6 times 14, and that's just ordinary arithmetic. That's not a dot product. That's just 6 times 14. And then take care of the vectors. K hat dotted with j hat. Well, k hat and j hat are perpendicular, so you'll have the cosine of 90 degrees in there. That's going to be 0. So this will be 0. And we've got a whole lot of 0 products in here because I hat dotted with I hat, that's 1. Remember, it's the magnitude of I hat, which is 1, times the magnitude of I hat, which is 1, times the cosine of 0, which is also 1. So this one is just going to be 30. But here I'll have I hat dotted with j hat. That's 0. And then I'll have I hat dotted with k hat. That's also 0. So out of this first set of products that I'd have, 3 different dot products, only the first one counts. When I get to this one, j hat dotted with I hat is 0, j hat dotted with k hat is 0, but j hat dotted with j hat is 1. So the middle term on here is going to be negative 4 times 7, so this will be minus 28. And then this last term, I've got a k hat dotted with I hat, that's 0. K hat dotted with j hat, that's 0. K hat dotted with k hat is 1. And I'll have negative 6 times negative 12. I think that's plus 72, if I remember right. So that complicated dot product that we just got here, 30 and 72, is 102 minus 28, which is going to be 74, I think. Oh, because 30 minus 28 is 2 plus 72 is 74. Okay, there's an easier way to do that. All right, in general, here's how it works. If you have a vector A, which has an x component in the I hat direction and a y component in the j hat direction and a z component in the k hat direction, and a vector B, which is comparable, it's got a x component in the I hat direction plus a y component in the j hat direction and a z component in the k hat direction. And by the way, any of these components, bx, by, bz, ax, ay, az, could be positive or negative. They could have units, could have all kinds of stuff. But a dotted with b will equal a sub x, b sub x plus a sub y, b sub y plus a sub z, b sub z. And so that makes it kind of easy to do almost in your head. Well, at least when they're integers. You can do them in your head, the dot product. And so you can come up with these things fairly simply. Okay, here are a couple of vectors. D and E, let's calculate the dot product according to that thing we just did. D dotted with E. I just take the X components, multiply them together, and I get 20. The Y components multiplied together, I get negative 8 times 2 is 16. The K hat components, or the Z components, 4 times negative 1 is minus 4. And so when I do that, I get 0. Well, what does that tell me? It tells me these two vectors are perpendicular. I wouldn't have known that looking at these things. They're in 3 space, three-dimensional space. I'd have a hard time drawing them. Maybe if I had some kind of a three-dimensional coordinate system and I could put them in there, I'd be able to see that. But this told me that instantly, that the two things are perpendicular. The dot product is a quick way to get the angle between two vectors. In 2 space, it's maybe not quite as useful. In 3-dimensional space, it's really hard. There isn't an easy way to tell if two vectors are perpendicular to each other, or there isn't an easy way to get the angle between two vectors except by going with the dot product. And so that's a much easier way to do it. All right, that is an introduction to the dot product, a bare introduction to the cross product. You can read more about that. The textbook does a pretty good job of explaining the dot product and talking about a lot of different things that I didn't address here, so you might want to read that. But now we're ready to start studying two-dimensional motion.